When a new AI model drops, the question that matters for most teams is not the leaderboard score. It is whether your stack can run it reliably, what it costs at your traffic scale, and which shortcuts will break in production. Today, we connect that headline to the engineering trade-offs behind the hype. You are likely seeing more production incidents lately. They look like network flakiness or logic bugs, but they aren't. The most common explanation, that models simply hallucinate, is a red herring. The real culprit is what I call the determinism gap. This occurs when engineers treat probabilistic GPU outputs as if they were deterministic CPU logic. We are applying standard exception handling patterns to non-deterministic AI agents, causing fragile systems where error recovery mechanisms fail against inherent randomness. Consider the data from recent behavioral studies involving over 1,300 participants. The findings reveal a dangerous bias known as the faith trap. When users treat predictive models as authoritative facts rather than probabilistic suggestions, their decision-making scope narrows significantly. In these scenarios, we observed that individuals were 3.39 times more likely to forgo guaranteed rewards in favor of AI predictions. Even after repeated prediction failures, this behavior persisted. The financial impact was severe, with losses ranging from 10% to 43% across the participant group. This is not just a user error, it is an engineering failure where we design systems that encourage blind trust instead of probabilistic verification. The core issue lies in how our current stacks handle uncertainty. Traditional software relies on strict logic: if input X, then output Y. We build try-catch blocks to manage the rare cases where things go wrong. But when you introduce a large language model running on specialized hardware like GPUs or TPUs, that predictability vanishes. The same prompt can yield different results every time because these accelerators are designed for speed and parallelism, not deterministic repeatability. We are trying to force probabilistic outputs into a framework built for certainty. This mismatch means our standard debugging tools become useless. When the system fails randomly, you cannot trace it back to a specific line of code or a network timeout. You are looking at a fundamental architectural incompatibility between hardware capability and software design patterns. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This leads us to a growing problem known as knowledge debt. As agentic AI accelerates code generation, we face two distinct types of erosion: comprehension debt and intent debt. Comprehension debt refers to the loss of deep understanding regarding how generated code works because the logic is opaque or complex. Intent debt is even more insidious. It is the erosion of the business rationale behind decisions. In traditional software development, when a bug appears in production, humans learn from it. The developer understands why the fix worked and updates their mental model for future iterations. However, AI agents do not retain context or decision history between sessions. They generate code based on immediate prompts without building long-term institutional knowledge. This breaks the critical feedback loop that human engineers previously provided to improve system resilience over time. The stakes are even higher when we look at productivity metrics across major economies. Data from OECD nations shows a stark reality about how AI is currently being integrated into production workflows. While high AI intensity explains only 31% of total factor productivity variance, the interaction between AI and convergence capacity accounts for 86%. Convergence capacity here refers to the human ability to integrate probabilistic outputs effectively. Essentially, we are pouring massive resources into tools that do not yield proportional gains because our teams lack the cognitive mediation required to bridge human intent with machine probability. We are stuck in a phase of augmentation where we simply slow down old workflows by adding new AI tools without redesigning them for the unique constraints of probabilistic systems. To move forward, we must shift from augmentation to reconstruction. This is not about writing better prompts or increasing context windows. Those address symptoms, not the root cause. True resilience requires a fundamental architectural pivot where uncertainty becomes a first-class citizen in your system design. Instead of trying to force AI into deterministic logic pipelines, you need to rebuild workflows around continuous monitoring and auditable constraints. The choice is no longer between speed and accuracy. It is between fast failure and reconstruction. Teams that attempt the former by treating AI as deterministic will see rising incident rates. Those who adopt the latter unlock the 86% of productivity variance currently locked away in their team's cognitive gaps. The path forward involves explicitly defining probabilistic boundaries within your architecture. You must introduce human-in-the-loop verification for critical paths, ensuring that high-stakes decisions are never fully automated without a safety net. Furthermore, you need to audit the intent behind code generation regularly. This prevents intent debt from accruing silently while your team loses sight of why certain architectural choices were made in the first place. By treating probability as an engineering constraint rather than a bug to be fixed, we can align our software stacks with the reality of modern hardware acceleration. Your current engineering judgment is evolving. The reliance on standard exception handling and if-then logic that served you well for decades is becoming obsolete for probabilistic workloads. To remain effective in this AI era, you must stop treating large language models as functions that return consistent results. You need to start designing systems where uncertainty is managed explicitly through architecture rather than hidden behind layers of assumption. The goal is not to eliminate the randomness inherent in these accelerators, but to build robustness around it. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.